It's my pleasure to be here to share our work, Fregata, a fast homomorphic evaluation of AES via TFHE. My name is Benqiang Wei. This work was joined with Rida Wang, Xianhui Lu, Xianhui Lu, and my advisor Xianhui Lu. Now I'm a PhD student from the Institute of Information Engineering, Chinese Academy of Sciences. So let's start it. And my presentation is divided into these three parts. First, I want to show a little background about homomorphic encryption. Homomorphic encryption is a very powerful technique to protect privacy because it can evaluate arbitrary functions on encrypted data without decryption. A typical application scenario for FHE is that the client can send the ciphertext encrypted by FHE to the client, and the client server can compute some practical functions on the encrypted data. Finally, the client received the ciphertext and decrypted the ciphertext and obtained the final result. That is FM. However, there are two problems in current applications of FHE. First, the low computational efficiency, because in real life, computational texts are usually complex and diverse. And the second one is large FHE ciphertext expansion. This is because most FHE schemes are based on LW or RLW problems. So FHE ciphertext expansion radius would up to about 3 to 6 orders of magnitude larger than the original plaintext size. So this would cause very huge transmission cost. An effective solution to solve FHE ciphertext expansion is to use hybrid homomorphic encryption. It is also called transciphering. Specifically, in HTTP frameworks, instead of directly encrypting the data with FHE, the client can encrypt the data using symmetric encryption scheme such as AES rather than FHE scheme, and then send the symmetric ciphertext to the server. What the server needs to do is to convert the symmetric ciphertext to homomorphic ciphertext by evaluating the decryption functions of the symmetric encryption scheme homomorphically. In this way, the cipher size expansion can be reduced to only one because we use the symmetric encryption scheme rather than FHE scheme. As we can see in HTTP frameworks, if the server want to perform homomorphic evaluation on ciphertext, the server must evaluate the decryption circuit of a symmetric cipher. So the selection of FHE scheme and the symmetric cipher is very important. Currently, there are two research directions in HTTP community. First, we can choose well-studied and standardized symmetric algorithms such as AES, but due to its deep multiplication depth, AES is generally not considered suitable for HEG framework. And the second one is many works trying to design FHE-friendly ciphers, such as Rust, like a cipher designed for BGV or BFA schemes, and Hero or Roboto ciphers designed for CKKS, and Elizabeth ciphers is designed for TFHE. And their goal is to design secure FHE-friendly ciphers with low multiplicative complexity and low multiplicative depth. However, some recent attacks against FHE cipher raised concerns among researchers about these new ciphers, and I think there is still a long way to go to see whether these ciphers can be practical or standardized. So in this work, we still focus on the standardized cipher AES. In this work, we give a fast homomorphic evaluation of AES using a very good strategy. Because AES is a list block cipher standard known for its efficiency and common use in various applications to protect sensitive information. Now I want to give a little background about AES. For AES 128, it consists of 4 operations: subbytes, shift rows, and max columns, and add round case. In these 4 operations, only subbytes is a nonlinear operations, which is 8 to 8-bit Xbox local table, while the other 3 operations are linear operations. So during the homomorphic evaluation of AES, I think there have 2 challenges. The first one is how to compute the nonlinear function subbytes, because it is unfriendly for FHE. And the other is how to deal with high multiplication depth, because we for AES 128 we must perform 10 runs to finish it. Now there are a lot of works that has presented homomorphic implementations of AES based on different FHE schemes. Yeah, for example, in 2012, Gentry presented the first homomorphic evaluation of AES based on the BGV, and recently the homomorphic evaluation of AES based on CKS and TFHE has been proposed, and they used very different techniques to compute the AES according the characteristic of the FHE scheme. So in our paper, we give a fast AES evaluation based on the TFHE scheme, but we explore a very different strategy. Before presenting our works, I want to give you some background about TFHE because our evaluation is based on TFHE. So you guys can follow me. In the TFHE schemes, we have three cipher types. The first one is TLW. TLW can encrypt a Scala message. And the second one is TRW ciphertext, which encrypts a polynomial message. And the third one is TRDSW. TRDSW ciphertext is usually used as the bootstrapping key in TFHE scheme. And we have some very important building blocks. The first one, such as external multiplications. External multiplications is the multiplication of TRDSW ciphertext and TRLW ciphertext, and its output ciphertext is TRLW. And we have a very important gate that it is called Simius gate. Simius gate can be constructed by external multiplications. And we have sample extraction. Sample extraction means that we can extract TLW ciphertext from TRLW ciphertext. And we have another very important operations, key switching. Key switching means that we can switch the security key from our ciphertext, such as we can switch TRW to TRW, or we can pack one or some TRW ciphertext to TRW ciphertext, and we can also switch the security key of TRW. And in TFHE schemes, we have very important operations that is blind rotation. In a word, blind rotation, it means we can rotate the text polynomial. Now I want to show some bootstrapping types in the TFHE schemes. The first one is identity bootstrapping. Identity bootstrapping means we can keep the message still while refreshing the noise. And the gate bootstrapping. Gate bootstrapping means that we can perform some gate operations while refreshing noise, such as XOR and gate, and functional bootstrapping, or it is also called programmable bootstrapping. Functional bootstrapping, it is more powerful because it can evaluate arbitrary function lookup table while refreshing the noise. And we have a more powerful bootstrapping that is called multi-value bootstrapping. Multi-value bootstrapping means that we can evaluate multiple functions at the same time using just one bootstrapping. And I want to introduce a very important bootstrapping type, that is circuit bootstrapping, because circuit bootstrapping plays a very important role in our work. Circuit bootstrapping means that we can convert TLW ciphertext to TRDSW ciphertext. So so during the homomorphic evolution of AES, we have some observations. As we all know, message encoding and evaluation strategies are very important in TFHE. So as we all know, message encoding and evaluation strategy are very important in FT. In around our computation, our AES algorithm, linear and nonlinear functions are used. Linear functions can be evaluated very quickly just by setting the plain text modular to 2, while nonlinear functions can be the sub-bias is usually considered the most difficult part to deal with. Our idea is to use efficient Smith gate to finish this step. This is because a single Smith gate takes only a few tens of microseconds, and it's very cheap. So now let's look at the efficient evaluation of Xbox. We combine the Smith gate and the mixed packing method to evaluate the Xbox. Specifically, for the 8 to 8 bit Xbox lookup table, we can list all the inputs and outputs, which means we have 256 lines. And don't forget that this table is publicly available, and if it can be viewed as plain text, yeah. And suppose the dimension of the ring polynomial is n equals 1024. So we can then we can pack all the output, this output of Xbox into coefficients of polynomials. So 2 polynomials are enough to pack all the output values, and we can notate them T0 on the T1. And first, we use the most significant, now x1 to x0 is that is our input, and x7 is the most significant of the input. So the first we use the most significant bit x7 to select the ciphertext where the target is located. That is T0. And after that, we use x0 to x6 to route the result, and that is the green box, to the first 8 coefficients of the plain text. And finally, we can extract them in turn using the simple extraction algorithm. And the detailed algorithms can be found in our paper. And this slide shows the detailed algorithms. And however, it must be noted that x0 to x7 are selected ciphertext, and they must be in the form of TR-GSW ciphertext, because we use the Smith gate. So when performing the next round of AES, we must to convert the TRW to TR-GSW in order to perform the next lookup table. This requires circuit bootstrapping. Circuit bootstrapping means to convert TLW ciphertext to TRGSW. So now let's see how we can achieve this ciphertext conversion. In fact, TRGSW ciphertext is more structured. Each of its rows is a TRLW ciphertext. If we decrypt each line of TRLW ciphertext, we will find that the first L line of TLW message are related to the secret key S. And the second L line of TLW are not related to secret S. So the specific conversions process can be realized by two steps. The first one is PBS LUT. PBS and many LUT it is a kind of multi-value bootstrapping, and that means we can evaluate multiple functions at the same time, just using one bootstrapping. And the second step is we can use private key switch to convert TLW ciphertext to TRLW ciphertext. In this way, we can construct this TLW into TRGSW ciphertext. However, it must be noted that in order to realize the free computation of XOR, we divide the torus into two parts. In other words, the addition is XOR operations. So we must to carefully design the text polynomial px to satisfy the cyclic property for PBS LUT. PBS many LUT is proposed in Asia Crypt 2021. In conclusion, we proposed Fregata fast homomorphic evaluation of AES via TFHE. And if you want to evaluate sub-bytes, we can use very cheap Smith gate to evaluate them at level 1. And for add round key, shift rows, and mix column, we can give almost free application at level 0. Here, different levels means that we use different encryption parameters to tolerate noise. So we can also apply this evaluation frameworks to Chinese block ciphers centered SM4. SM4 use the general festival structures, and it's not like unlike AES, it runs up to 32, so it has higher multiplication depths. And in addition, in the homomorphic evaluation of SM4, the cipher test noise generated in the current round is cumulative with the previous cipher noise. So after some rounds, it will lead the cipher test decryption failure. So we add identity bootstrapping to refresh the noise to solve this problem. So so now I have covered the core technique about Fregata, but now I would like to show our recent improvement about this work. And we noted that AES algorithms can be implemented in a variety of ways, which is dependent on implementation environment. Yeah, in addition to executing these four basic functions sequentially, we can also merge subbytes, row shapes, and the mixed columns. These three functions into 8 to 32 bits lookup table as follows. This kind of applications bring some advantages in our homomorphic evaluations, such as we will need a smaller evaluation k size. As just mentioned, we can still efficiently evaluate the 8 to 32 lookup table. Since the number of the bit in the input remains 8. This is the same as before. So this means that the number of circuit bootstrapping is would not increase. So the computational cost would hardly increase. And although all functions in AES now can be efficiently evaluated, but now circuit bootstrapping becomes the efficiency bottleneck in our framework. So, and we observe that circuit bootstrapping can be further optimized because in the second step, the first L row of TRW ciphertext of TRDSW can be constructed by the second arrows of TRW. This operation is called AES square multi-mult. This is introduced by KM in 2023. Essentially, it is a kind of key switch. And this operations is more efficient than the previously used private key switch. So AES can be evaluated for the efficiently. And this diagram shows the detailed evaluation process. In this diagram, you can see that add-on key, shift rows can be evaluated at level 1, while 8 to 32 or 8-bit lookup table can be evaluated using CMS gate. And we use PBS many lookup table and public key switch, and it was square mult techniques to accelerate the conversion of TRW to TRDSW ciphertext. Finally, I would like to show the efficiency performance. It is worth noting that we use a very special public available FHE library that is TFHE because it supports PBS, many lookup table technique. And in original paper, our evaluation, let's see, for an AES block was about 86 seconds with for the operation optimization, we can reduce it to about 46 seconds. However, as we can see from the table, the latest time means amortized time. So the amortization time of our work is still much higher than the evaluation based on BGP or CQS. Yeah. So here are some reference. That's all. Thank you. And the code can be found in this home page. Thank you. Thank you.